At the end of this video, you should be able to describe Kepler's law of planetary motion, relate Newton's mathematical analysis of gravitational force to the elliptical planetary orbits proposed by Kepler, and solve problems involving orbital speed and period. Chapter 7, Section 3, Motion in Space. Kepler's Laws. People have studied the motions of the planets since ancient times. Until the middle of the 16th century, most people believed that Earth was at the center of the universe. Originally, it was believed that the Sun and the other planets orbited Earth in perfect circles. However, this model did not account for all of the observations of planetary motion. In the 2nd century CE, Claudius Ptolemy developed an elaborate theory of planetary motion. Ptolemy's theory attempted to reconcile observation with theory and to keep Earth at the center of the universe. In this theory, planets travel in small circles called epicycles, while simultaneously traveling in larger circular orbits. Even Ptolemy's complex model did not fully agree with the observation, although the model did explain more than previous theories. In 1543, the Polish astronomer Nicholas Copernicus published on the revolution of the heavenly spheres, in which he proposed that Earth and the other planets orbit the Sun in perfect circles. Figure 3.1 of your text shows a sun-centered planetary model that is believed to have been made for King George III of England. The idea of a sun-centered universe was not completely new in the 16th century. A Greek named Aristarchus theorized 1700 years before Copernicus that Earth revolved around the Sun, but most other scientists did not accept this theory. Kepler's 3 laws describe the motion of the planets. The astronomer Tycho Brahe made many precise observations of the planets and stars. However, some of Brahe's data did not agree with the Copernican model. The astronomer Johann Kepler worked for many years to reconcile Copernican theory with Brahe's data. Kepler's analysis led to 3 laws of planetary motion, which were developed a generation before Newton's law of universal gravitation. Kepler's 3 laws can be summarized as follows. Kepler's first law states that the planet's orbits are ellipses rather than circles. Kepler discovered this law while working with Brahe's data for the orbit of Mars. While trying to explain the data, Kepler experimented with 70 different circular orbits and generated numerous pages of calculations. He finally realized that if the orbit is an ellipse rather than a circle, and the Sun is at one focal point of the ellipse, the data fit perfectly. Newton's second law states that an imaginary line from the Sun to any planet sweeps out equal areas in equal times, as is shown on the screen here. In other words, if the time a planet takes to travel the arc on the left, which is delta t1, is equal to the time the planet takes to cover the arc on the right, delta t sub 2, then the area A1 is equal to the area A2. It is easy to see from this figure that planets travel faster when they are closer to the Sun. While Kepler's first 2 laws describe the motion of each planet individually, his third law relates the orbital periods and distances of one planet to those of another planet. The orbital period, big T, is the time a planet takes to finish one full revolution, and the distance, r, is the mean distance between the planet and the Sun. Kepler's third law relates the orbital period and mean distance of 2 orbiting planets as follows. T sub 1 squared divided by T sub 2 squared is equal to R1 cubed divided by R2 cubed, or orbital period squared is proportional to mean distance cubed. This law also applies to satellites orbiting Earth, including our moon. In that case, r is the distance between the orbiting satellite and Earth. The proportionality constant depends on the mass of the central object. Kepler's laws are consistent with Newton's law of gravitation. Newton used Kepler's laws to support his law of gravitation. For example, Newton proved that if force is inversely proportional to distance squared, as stated in the law of universal gravitation, the resulting orbit must be an ellipse or a circle. He also demonstrated that his law of gravitation could be used to derive Kepler's third law. The fact that Kepler's law closely matched observations gave additional support for Newton's theory of gravitation. Kepler's third law describes orbital period. According to Kepler's third law, t squared is proportional to r cubed. The constant of proportionality between these two variables turns out to be 4 pi squared over big G m, where m is the mass of the object being orbited. Thus, Kepler's third law can also be stated as follows. T squared is equal to quantity 4 pi squared over big G m multiplied by r cubed. The square root of the above of that equation, which is shown on the screen here, describes the period of any object that is in circular orbit. The speed of an object that is in a circular orbit depends on the same factors that the orbit does, as is shown in this equation. The assumption of a circular orbit provides a close approximation for real orbits in our solar system, because all planets except Mercury have orbits that are nearly circular. Note that m in both equations is the mass of the central object that is being orbited. The mass of the planet or satellite that is in orbit does not affect its speed or period. The mean radius, r, is the distance between the centers of the two bodies. For an artificial satellite orbiting Earth, r is equal to Earth's mean radius plus the satellite's distance from Earth's surface, or its altitude. Figure 3.3 on the screen here gives planetary data that can be used to calculate orbital speeds and periods. At this point, you should be able to understand sample problem D. Weight and weightlessness. In the chapter about forces, you learned that weight is the magnitude of the force due to gravity. When you step on a bathroom scale, it does not actually measure your weight. The scale measures the downward force exerted on it. When your weight is the only downward force acting on the scale reading is equal to your weight. If a friend pushes down on you while you are standing on the scale reading will go up. However, your weight has not changed. The scale reading equals your weight plus the extra applied force. Because of Newton's third law, the downward force you exert on the scale equals the upward force exerted on you by the scale, the normal force. Thus, the scale reading is equal to the normal force acting on you. For example, imagine you are standing in an elevator, as is illustrated on the screen here. When the elevator is at rest, as is shown in portion A, the magnitude of the normal force is equal to your weight. A scale in the elevator would record your weight. When the elevator begins accelerating downward, as in portion B, the normal force will be smaller. The scale will now record an amount that is less than your weight. If the elevator's acceleration were equal to free fall acceleration, as is shown in portion C, you would be falling at the same rate as the elevator and would not feel the force of the floor at all. In this case, the scale would read 0. You still have the same weight, but you and the elevator are both falling with free fall acceleration. In other words, no normal force is acting on you. This situation is called apparent weightlessness. Astronauts in orbit experience apparent weightlessness. Astronauts floating in a space shuttle are experiencing apparent weightlessness. Because the shuttle is accelerating at the same rate as the astronauts, this example is similar to the elevator, which is shown on the screen here. The force due to gravity keeps the astronauts and shuttle in orbit, but the astronauts feel weightless because no normal force is acting on them. The human body relies on gravitational force. For example, this force pulls blood downward so that the blood collects in your veins of your legs when you are standing. Because the body of an astronaut in orbit accelerates along with the space shuttle, gravitational force has no effect on the body. This state can initially cause nausea and dizziness. Over time, it can pose serious health risks, such as weakened muscles and brittle bones. When astronauts return to Earth, their bodies need time to readjust to the effects of the gravitational force. So far, when we have been discussing apparent weightlessness, actual weightlessness occurs only in deep space, far from stars and planets. Gravitational force is never entirely absent. But it can become negligible at distances that are far enough away from any masses. In this case, a star or astronaut would not be pulled into an orbit, but would instead drift in a straight line at constant speed. At this point, you should be able to describe Kepler's laws of planetary motion, relate Newton's mathematical analysis of gravitational force to the elliptical planetary orbits proposed by Kepler, and solve problems involving orbital speed and period.